This sample is actually gallium, and gallium is actually my favorite chemical element because it does look very much like mercury. You can see it's a liquid, but it's not at room temperature. It's very close to my body temperature. This will melt. I can get this metal to melt in my hand because it melts at 85.6 degrees Fahrenheit. So a warm hand can make a sample of gallium in its liquid form. Fascinating element, and it's very safe. It will just tarnish my hand a slight grayish color that will easily just wash right off.
Ever wonder what happens if you put 1,000 amps through a coin? Well, there's one way to find out. Wow, that's hot.
Ever wonder why when you're looking at a helicopter or anything that's spinning and it doesn't really look like it's spinning, but you know it is? Well, that's just because of the frames per second that we see with our eye as well as the camera. So let's go ahead and do an example. We've got our bike tire, and obviously if it spins, you see it spin. But if we spin it fast enough to the point where our frames per second aren't catching it, but they're only catching in between, it's gonna look something like this. And as it slows down, it'll look like it's actually speeding up. So if we stop that and we do it one more time, you can see it look like it's steady, and then as it slows down, it'll start to move because your eye is starting to finally capture what's really happening.
If this were the actual size of Mercury, Venus, Earth, and Mars, then that would be the actual size of the sun. By the way, on this scale, Pluto would be the size of a plum. I'm just saying.
This is my telescope, and this is a solar filter. What the solar filter does is it actually blocks out all the light so you can see the sun without all the light blocking it. Now let's see what it looks like when you put a solar filter on a telescope, and let's check it out. So here's a picture that I took, and on the top right you can actually see a sunspot, and if you use an H-alpha filter, which you can see here, you get a lot more detail about the sun.
This video shows a neutrophil, a type of white blood cell chasing Staphylococcus aureus, the bacteria that causes staph infections. Two of them actually, the two little black spheres there running away from the neutrophil. You can see the waves of contractions going through the neutrophil as it chases it. It's not exactly clear which chemo attractant the neutrophil is following. It doesn't have eyes, obviously, but it may be an innate immune protein like complement protein C5a, which can be triggered by antibody binding. Mission accomplished.
So NASA scientists just discovered a parallel universe where time runs backwards. I mean, did they really, or what's going on? High energy particles hit the Earth every day. Sometimes it's from solar winds and sometimes it's from other things. Low energy particles like neutrinos can pass through the Earth, but high energy particles cannot. Basically, they hit solid ground and stop moving. So what NASA did was they set up some super sensitive radio equipment. Then they expected to only be able to measure particles going down into the Earth. But turns out they did capture a particle coming up from the Earth. This particle was a tau neutrino and definitely way too heavy to be coming up from the Earth. So the theory that the media is talking about is that a particle was about to hit the Earth, then it changed into a different particle, went through the Earth, and then changed back into a tau neutrino and went through the electronics. Somehow this means parallel universe, but it's not the only explanation. For one, this station named IceCube detects tau neutrinos, and it didn't detect nearly enough neutrinos to expect any of them to go through Earth. It could have just been an experimental error. This paper is showing how ice is distorting the cosmic rays. There's a few other options, but of course, a parallel universe would be pretty cool.
Here's a fun experiment you can do at home. If you mix Arm & Hammer baking soda with vinegar, you get CO2. We're capturing that CO2. It's coming up here through this tube and into our cup. If I take that CO2 and I pour it on these candles, boom! They go out. That was pretty sweet, but let's go bigger.
Everybody shake, 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 shake.
We're gonna seal these edges so they're airtight. We're gonna add a full pound of baking soda to each bucket. We're then gonna add a liter of vinegar to each bucket. You can hear it forcefully coming out. Get all that CO2. 3, 2, 4. Oh! Yes! What? Reigning champion of putting out candles. Ugh.
Ever wonder if fire conducts electricity? Let me light those matches there and find out. But how do I do that without being zapped? How about with a giant laser? So check it out. Fire is definitely a conductor. Pretty cool, right?
This is bromine. It's chemically very similar to chlorine, except chlorine's a gas and bromine's a liquid. It also lets off a lot of nasty orange vapor, and this is why I sealed it in glass. Bromine's really dense, and it's more than 3 times as dense as water, and this makes its vapor really heavy. Bromine's notoriously difficult to store, and if I just put it all back into a bottle or something, it would damage everything around it. So I have to seal it again in a glass ampule that I made from a test tube.
One of the biggest lessons I've learned as a physics student is that absolute truth does not exist in science. For example, think of a current in a wire. At first you learn about this effect as electrons rushing down the wire close to the speed of light. When you learn more about metals though, you find out that actually the electrons bounce around randomly off the nuclei so that their net movement is normally 0, and applying an electric field just adds a small net effect that propagates near the speed of light. If you applied quantum theory, you'd know that the electrons aren't really bouncing, but their wave functions scatter off the Coulomb potential of the nucleus, and so on. You could go deeper and deeper and describe the phenomenon more and more accurately, but it's never going to be perfect, and we really don't know for sure that it's even all right. It's just a model that best fits all the evidence, and it's never failed, so we follow it. But really, most of the time you want to describe a current in practice, it works best just to go back to the first order approximation.
Here's a project you can do inside with your kids. Cheap, safe. Get a couple of cups, wrap the tape around the middle. Rubber band. You can make longer. This happens to be too long rubber bands. Put your thumb on the rubber band, wrap it around once, twice. What this is, the Magnus effect, and it teaches that there's a lower pressure on the top side, which causes things to rise, which is what happens with golf balls.
This is nitric acid, and it's one of the few acids that can react with copper. But oddly enough, it doesn't work well when the acid's pure. This is because of something called passivation, where a layer of oxidized copper forms and it covers the surface and protects the rest of the copper. To get it going, I have to add some water, which will dissolve the protective layer and let the acid attack it. This more dilute acid can completely shred the copper, and all the metal should eventually disappear.
Now this is my favorite recent experiment. It takes some hot water from the tap, not boiling water, just hot water, and a syringe. Now at sea level, water boils at 100 degrees, but if you can find a way of reducing the pressure, for example, like on Everest or something like that, then you can actually make it boil at a lower temperature. Now, we haven't got Everest here, but if I suck up about 2 milliliters or so water into the syringe, now look at this, if I cover it up and actually reduce the pressure by sucking it up, look what happens to the water. It actually starts to boil. I think it's really cool.
These are car ignition coils. They use high voltage to ignite fuel in an engine. Check out what happens when I connect them to this blank circuit board. Alright, here we go. Pretty cool, right?
So a lot of you were curious what chemical makes a white flame, and let me show you what it is. The chemical that makes a white flame is known as nitromethane, and something interesting about it is when you try to light it on fire, you actually can't light it on fire. So what you need to do is add a little bit of alcohol to it, just a little bit, and then it'll catch on fire. Now compared to a normal orange flame, you can tell that it's much whiter. It's almost like a ghostly white flame. It's also a super energetic flame. I mean, pound for pound, it contains 8 times the energy as gasoline. No wonder they use it as a race car fuel.
This is a strange property of water that happens on a hot pan. As you heat up a pan on the stove, water boils off faster and faster until it gets to a point where the water acts completely different. The water starts to bead up as if it's levitating. This is called the Leidenfrost effect, and it happens when the pan reaches above about 350 degrees Fahrenheit. If you add a little bit of food coloring to the water, you can see the effect even better. The Leidenfrost effect happens because the water on the bottom of the droplet boils off so fast, it creates this layer of vapor. The vapor acts like a cushion, almost allowing the water to levitate. That's some cool physics.